So thank you for having me. I wish I could have been there in person, but I just had a baby a few months ago, so not quite ready to travel yet. Um, but I'm going to talk about JWST observations of AGB stars. And some of this might look familiar to those of you who might have been at the Rome meeting a few weeks ago, because my postdoc, Elizabeth Tarantino, was there and gave a talk on a similar topic with some of the same results. So you'll get to hear it twice. So here we go. Is this going to work? There we go. All right, so when you're talking about JWST, you're going to end up talking about dust, right? So that's what I'm going to focus on is how much dust do AGB stars contribute to the ISM? And first, I'm going to give some background of where we are up to the launch of JWST using Spitzer and Hubble data. So I'm going to talk about M31 and M33. I'm going to talk about the Magellanic Clouds and some other local group dwarf galaxies. And just to give you the punchlines right up front, we're seeing that metal poor AGB stars can create dust as early as 30 million years after forming, which means that they are important dust producers for the early universe. We're seeing that they are contributing a significant fraction of the ISM dust, or they can contribute a significant fraction of the ISM dust. And their dominant chemistry shifts with metallicity, which is not that surprising, but it's occurring in some somewhat surprising ways. So I'll start with just reminding everybody who the dust producers are, which are primarily coming from supernova and AGB stars. There's also ISM grain growth, but I'm not going to talk about that right now. So we know that supernova can make dust, and the best example of that, or a lot of everybody's favorite example, is supernova 87A, which this is a JWST image here. And there were ALMA observations a number of years back that showed this huge dust cloud. So we know that supernova are making a huge amount of dust. But the problem is that in this particular case anyway, the reverse shock still hasn't hit this dust cloud in the center. And so at least some of this dust is going to eventually get destroyed before it can make it to the ISM. We don't know how much yet, but that's the big question. Are supernova net creators or are they net destroyers of dust? Because they're also going to destroy pre-existing dust that was already there, right? But AGB stars, on the other hand, they all have this dust producing phase, and all of that dust survives, or at least most of it survives, right? So which one is dominating? And if you look at pre-solar grains in the solar nebula, you'll see that the dominant source of dust is coming from AGB stars. And this is the breakdown in these pie charts here, showing the fraction that's coming of different kinds of dust grains that are coming from AGB stars and supernova. The dominant type of dust is in the middle, silicates and oxides. So that's dominated by AGB stars. And according to this recent paper from Hospital, about 75% of the dust is coming from AGB stars in the solar system. And this dust is primarily oxygen rich. So that's what it looks like in our own neighborhood. But when you go to high redshift, the story changes a little bit. And this is something that has been called the high redshift dust budget crisis. And what this refers to is that in high redshift galaxies, there are these massive dust reservoirs, and nobody knows how you can make that much dust that early in the universe. And most of the models of AGB dust yields have predicted for years that AGB stars don't make enough dust fast enough to explain these dust reservoirs. And this is just an example on the right from Rollins et al. Showing a few different models of dust yields. And they would need to have yields high enough to cross this blue bar up here in order to be enough to explain the amount of dust in this particular galaxy. And they don't. Maybe a teeny tiny bit right here from this one model, but most of them don't. And so the solution has been for a number of years now to attribute the dust to supernova and ISM grain growth. So very different from what's going on in our solar system. But this has been sort of an accepted solution for the most part. However, I will say that there have been models recently, and I have just a couple examples down here, Zukovska and Deleuze et al., that show that AGB stars actually can dominate in the models depending on some different conditions. You know, what is the what is the star formation history? What is the age? What is the metallicity? And in certain situations, the AGB stars can dominate even over grain growth. But this is the models, right? So what do the data tell us? And we can look at observations of nearby galaxies from the optical to the mid-IR to try to answer this question. And that's what I've been doing for a number of years now. And we have multiband photometry, so optical thermometry, are using mostly Hubble and Spitzer to observe a number of galaxies. And so I have a few listed out here that I'm going to talk about, from nearby dwarf galaxies to the more nearby SMC and LMC, and then M31, and this is listed in increasing metallicity. And I'll start over here at the highest metallicity with M31. And here we're using Hubble data from the FAT program and also Spitzer data, so about 0.5 to 24 microns. And this is a paper from Goldman et al. That used data from Hubble that observed about a third of the galaxy. So this is the footprint here. So it's a lot of data. And we have these medium band filters in Hubble that are really useful for AGB stars because they allow you to separate oxygen-rich stars from carbon-rich stars. And so the oxygen-rich AGB stars live over here with a nice sequence of increasing water absorption, and the carbon stars live over here, and you get this really clean separation. So we first used this to separate the different kinds of stars, and then we went to the Spitzer data. This is just an example color magnitude diagram over here, to try to estimate how much dust they were producing. And the conclusion from that paper was that the AGB stars look like they can account for up to about a third of the ISM dust in M31, so a pretty significant fraction. And almost all of it is oxygen-rich dust. And that's not that surprising, because that's what we see in the solar system. And we've known for a while that at high metallicity, you're more likely to have an oxygen-rich star than a carbon-rich star. But there are some surprising things going on at M31. And if you look at this diagram of the initial mass versus metallicity. Now this is, I think you saw a diagram similar to this from Ian yesterday. I didn't see his talk, but I think he was going to show something like this. And so it should be familiar, hopefully. But the idea is that there are different regions on this plot where you have carbon stars and different regions where you have oxygen-rich stars. And we don't know exactly where this boundary is. I'm just showing one particular set of models here. But this boundary is, it changes depending on which models you have. And if you're on this, if you're making a carbon star, you're making things like amorphous carbon, silicon carbide, magnesium sulfides. If you're on the oxygen-rich side, you're making silicates and other oxides. But in M31, you can actually count up the number of carbon stars compared to the number of oxygen-rich stars using the Hubble data that I showed on the previous slide, and compare that to other galaxies. So we've got metal poor local group dwarfs up here, and M33 here, where they follow this really nice trend. But when you get to M33, you follow this trend for a little while in the outskirts, but then as you get closer and closer to the bulge, it completely drops almost to zero. And so we think what's happening is that we're actually probing this boundary in M31, where you start to get to a point where you really can't make carbon stars anymore. And this is why we have a regime of almost all oxygen-rich dust in M31 and in places like the solar system. So this is the first time, I think, that this boundary has been so clearly demonstrated in a system. All right, so that's on the metal-rich end. So now I'm going to sort of move to the middle. Excuse me, I have a cough. I'm going to try not to cough directly into my microphone. So we have the LMC and the SMC here that were observed with Spitzer with the SAGE program. And so we have 3.6 to 160 microns. And in these galaxies, there's been a number of papers that have counted up all the AGB stars and tried to estimate how much dust they're making. And the initial papers that came out from this program said that about 2% of the ISM dust can be accounted for by the AGB stars. And this is just a plot of the different types of AGB stars and how much dust they're making as a function of luminosity. And it's dominated by carbon stars. But then there was Herschel observations of these galaxies, and the ISM dust mass actually decreased by a factor of 10 after those observations came out. And then after that, there were a little bit more scrutiny on these far infrared stars that the SAGE program had identified. And we had dismissed these previously because we thought they were mostly things like young stellar objects or unresolved background galaxies. But it turns out that there is a subset of them that are AGB stars, and these are just a couple example SEDs, and they're fit really well by AGB models. And when you include those, that increases the AGB dust input by a factor of 2. And then some new dust models came out for AGB stars not long after that. And if you plugged these models into our estimates, you would get an increased dust estimate by about a factor of 5. So when you take all of this together, today, you could say that AGB stars can account for most of the ISM dust in the Magellanic Clouds. It doesn't mean that they definitely do, but they could. They make enough dust that they could be a dominant source. And the dominant source, or the dominant dust species, is highly stochastic. About 5% of the total population of AGB stars is making all of the dust, or most of the dust, and that's in these extreme AGB stars, which are mostly carbon-rich, and these far-infrared stars, which are mostly oxygen-rich. But only 5% of that population is these oxygen-rich stars. So as you see here, there's only 17 of these far IR stars in the SMC, right, compared to 380 of the carbon stars. So it's highly stochastic. If you add a few more of these far infrared stars, you could totally change the balance. So it's not quite clear what's going to dominate at these metallicities. And then when you go to even lower metallicity, you can look at the dusting survey, which stands for Dust to Nearby Galaxies with Spitzer. And this is not nearly as much data. It's really only 3.6 and 4.5 microns with Spitzer because they're far away, so it's hard to get good data. But you find that when you plot the average dust production of the stars based on that color as a function of metallicity, you find basically a scatter plot. And what we were expecting naively was that we would have fewer or less dust at lower metallicity, right? But it's just a scatter plot, and some of these galaxies that have really low metallicities are making just as much dust as the LMC and the SMC stars. And so clearly, dust is forming very efficiently at low metallicity. Even in galaxies with metallicities as low as 1% solar. But there is a caveat here, and that is that these stars might all be low mass stars, which means that they might not be contributing to the early universe. And just to discuss that a little bit more, this is that same mass metallicity plot from before, and the stars that are in the dustings galaxies are probably in this range here, sort of lower mass, probably carbon stars. We don't know for sure because we only have a few data points, but we are probably in this regime. And these carbon stars are slow. They're low mass. They take hundreds of million years to start making dust. So they're not really that important at high redshift. But these stars up here, these are the ones that are interesting at high redshift, because if they can make dust, they evolve very quickly. But we think that they're mostly oxygen-rich stars, and oxygen-rich stars depend on the metallicity of the galaxy in order to make dust, unlike carbon stars, which are dredging up their own carbon and can make a lot of dust, right? So that's the big question, is can these massive oxygen-rich stars make dust at low metallicity? And we did go and look at some of these dustings galaxies with Hubble to do that same trick that I showed earlier with these medium band filters, where we could separate the stars by type, where the oxygen-rich stars are blue and the carbon-rich stars are red. And in these three galaxies on the bottom, these are the lowest metallicity galaxies that we looked at. And there are a handful of these very dusty oxygen-rich stars in blue, the ones that are circled in blue. And so that is really interesting. It's saying that there are some massive dust-producing oxygen-rich AGB stars in these galaxies. And it suggests that these could be important at high redshift. But we know very, very little about these stars. We know that they're dusty, and we know that they're oxygen-rich, and that's it. We don't know how much dust they're making. We don't know exactly what type of dust they're making. And that's where JWST is going to come in. But before I talk about JWST, I just want to point out that there are some models out there that are starting to show that even at low metallicities, so here is in magenta and blue are metallicities that are kind of similar to the galaxies that I was just showing you. The highest mass AGB stars are making almost as much silicate dust as the lower mass ones are making carbon dust. So, so the models are starting to come around to this idea. So now I'm going to jump into JWST observations, and I will start by talking about how you find the AGB stars and how you classify them with JWST, because that's the first step. So this is the JWST Stellar Populations Early Release Science Program. And the goal of this program really wasn't AGB stars. It was really to demonstrate point source photometry with JWST. And their primary deliverable was a PSF photometry package. So I just wanted to advertise this down here, that they have updated and released DOLPHOT, which is a program that's been used for a long time with Hubble to do photometry. And you can now use it for NIRCam, NIRISS, and MIRI. And one of the targets from this program was WLM, which is a star-forming nearby dwarf galaxy. The NIRCam observations are outlined here in white. And this is the data, and it is gorgeous. It goes incredibly deep with just a very short exposure time. And but the thing that is relevant to this talk is that this galaxy also has a handful of evolved stars way up here. And we also have the Hubble data of this region in these same medium band filters that can classify the oxygen-rich stars and the carbon-rich stars, and that's what's shown here. And so we had this sort of secondary question in this program of, can we, with the JWST filters, can we get a similarly clean separation of different stellar types with JWST so that going forward we can do this kind of analysis in even more distant galaxies? And so the data in WLM are shown here, and there are a couple different filter combinations, one on the left and one on the right. And the red stars are the ones that Hubble identified as carbon-rich, and the blue ones are the ones that Hubble identified as oxygen-rich. And you can see that the separation looks pretty good in these filters. There's a few outliers, and they're circled here, and they're discussed a little bit more in this paper that just came out this year. And so it's very promising. But there are a couple of caveats here, and if you look down at the lower panels, these are simulations that were created using the Colibri models from the Padua group, and we added a whole bunch more mass. So it's the same star formation history as WLM, but more mass. And the first thing to point out is that these models are doing a really good job. They're still not perfect. You can see, like, for example, here, the colors are a little bit different, but they look very similar to the data. And you do get good separation in the models as well. But if you add more mass, you do start to see some overlap here. It's not quite as clean as it was in Hubble. So we explored this a little bit more and found that there is a metallicity dependence here. So if you look at low metallicity, you get something like this, similar to what I just showed on the previous plot, where you get a lot of overlap. But as you go to higher and higher metallicity, things look much, much cleaner. So, so what we would say is that these filters are really useful for doing the same trick of identifying the stars in JWST, but you have to be a little bit careful as you go to lower metallicity. And we did also explore, so we only had data in a few filters, but we did explore with the models a few different filter combinations. Or actually, we looked at every combination, and these are the few that we pulled out that seem to do a good job in addition to the ones that we had data for. And some of them do a little bit better at low metallicity, like this one down here is a good one. But go and take a look at that paper if you want to see more details. So that's how you find the AGB stars. So now let's talk about dust. And for that, I'm going to turn to this program that's observing Sextans A with JWST. And we chose Sextans A because it is extremely metal poor. It's anywhere from 1 to 7% solar metallicity, depending on the age of the population. The RGB stars look like they're closer to 1%, and the ISM, the most massive stars, look like they're closer to 7%. And we know it has some ISM dust that's been detected. We know it has a large stellar population, so we can get some good statistics. We know it has recent star formations, so the stars are in about the right age for AGB stars. And we know it has some dusty stars, including some of these oxygen-rich dusty stars that we saw in Hubble and Spitzer. So this is that same plot that I showed a few slides earlier. And these three stars in particular are the ones that we're interested in. But of course, we actually have a much bigger field of view here, so we have more than what we saw with Hubble. So what we decided to do was basically throw everything we've got at this galaxy. So this is a couple of example SEDs of stars in the Magellanic Clouds. So an dusty oxygen-rich star and a couple of dusty carbon-rich stars. And we have 8 NIRCam filters, all the way from 0.7 to 4 or 5 microns. And then we also have 5 MIRI filters that go all the way out to about 20 microns. And we have some spectroscopy in the middle here of just 6 targets. And so altogether, we're going to have this really great data set of this population. And so just to show off what JWST can do, this is the Spitzer data that we had in Sextans A, and this is what we have now. It's a completely new world. We can do so much more now than we ever could with Spitzer. And this is what the photometry looks like. It's extremely deep, again, all the way down to the main sequence turnoff, just like in WLM, with a pretty modest exposure time. And we have a really sizable AGB population up here, including some red supergiants also. And we think that We have about 250 AGB stars, so that's not finalized yet. This is going to be in a work that's coming out by my postdoc, Elizabeth Tarantino. And by doing this, we can, by going this deep, we can get a good star formation history. And that's really important for then doing dust evolution models, which is sort of the next step in our analysis. And then this, as you go further into the infrared, so over here I'm showing near infrared, and on the right I'm showing out to about 4 microns. And you can see these red stars that we've highlighted are extremely red. They are very, very, very dusty. All the way out, colors of 8 in 1.5 minus 4.4 microns. So there is a ton of dust being formed in Sextans A. But we also have low resolution spectroscopy in this galaxy, and just 6 stars. So because this is a little bit expensive, so we could only do a handful of stars. And these are the 6 that we picked. They're all very bright and all very dusty. They were selected based on their Spitzer colors. And here's the spectra over here on the right. The first one up here is our only oxygen-rich star. It has this really deep water absorption. And then we have 5 carbon stars in the sample. And we know they're carbon-rich because they have this deep acetylene feature. And the carbon stars, at least, are showing what looks to be like a silicate carbide feature. There's a lot of noise over here, but this feature does appear to be real, and you can see it better in this plot here, where I'm showing one of the spectra compared to some spectra of other stars in the galaxy that have much cleaner data. And you can see that this feature is right where it should be. And when you measure the strength of it and compare that to what we're seeing in other galaxies, you get what's on the right over here. The stars are our 5 stars, and then all this other data is from the Milky Way, the Magellanic Clouds, and other nearby dwarf galaxies. And the strength of the silicate carbide in these stars is similar to what we're seeing in Magellanic Clouds, and in this particular star, even as strong as a star in the Milky Way. So these have a ton of silicate carbide, really, considering their metallicity, and that's really surprising. It's not entirely clear how you get this much silica for dust production at this metallicity, but it's there. And then our other star, our oxygen-rich star, let me go back to the spectrum real quick. So it's up here, and it really is not showing any signs of a silicate feature here around 10 microns. So there doesn't appear to be any silicate dust, but it is red. It's very dusty, or has a lot of infrared excess. And when you fit the SED with a dusty model, so the stellar photosphere model is the gray points here, and the JWST data are the blue points, and you can see that there's a huge infrared excess. And the dusty model is best fit with metallic iron grains. And so we can't say for sure that that's what we're seeing, because this is a featureless spectrum, and that's just how metallic iron works. So you can't really confirm that that's definitely what it is, but it does fit. And that's really interesting, because it might mean that these stars are making a lot of dust despite their extremely low metallicity, potentially at very early times, at 30 or 50 million years after they form, and that can be really important for the high redshift universe. And I do want to point out, this is not the first time that this kind of a spectrum has been seen in AGB stars. People have looked in, for example, globular clusters and seen similar things. And so metallic iron might be more common than has been previously thought. So we'll see. We're going to do similar fits for all of our oxygen-rich stars and see what we find in Sextans A. So that is what we're seeing in Sextans A. And I also want to point out, though, that there are a ton of programs with JWST that are looking at AGB stars. And I'm just listing some of them here. This is not a comprehensive list, but this is just the ones that I know the most about. And they're covering galaxies spanning a huge range of star formation histories and metallicities. And we'll be able to resolve the AGB stars and go well below the tip of the red giant branch and learn a ton of information. But it turns out JWST data is hard, and people are working hard to get this stuff out, but it's taking time. And so things are just starting to trickle out into the literature. And I just wanted to show these 2 papers. One is observing 6822, and one is observing, or did observe 1Ziggy 18. And these are some of their just examples of their data. So this, in 6822, they have these really beautiful color magnitude diagrams, and they've got their AGB stars labeled up here. And then they go into the infrared with MIRI, where they're getting lots of dusty stars. And then this one from Hirschauer et al. Is showing the evolved stars compared to the young stars. And their next steps of these programs are then to then do some SED fitting and estimate how much dust these stars are producing. So that is basically where we stand with dust production and AGB stars as far as Spitzer, Hubble, and JWST are concerned. I'll just summarize here. In M31 at the highest metallicity, we are seeing that AGB stars are contributing up to a third of the dust budget, and oxygen-rich dust is dominating. In the Magellanic Clouds, we see that the AGB stars, might be making about half of the dust budget, possibly more if we're generous, depending on our assumptions. That looks like the carbon-rich mostly dominates, but there are stochastics that makes the oxygen-rich also important. In the lower mass dwarf galaxies, we're showing that dust is forming very easy at low metallicity. It's mostly carbon rich, but that it does appear that there is at least a small population of these oxygen-rich stars that could be very important at high redshift. So stay tuned for more JWST results. We know that a lot of dust is forming at low metallicity, and we're still trying to understand whether or not there's enough oxygen-rich dust to explain these high redshift dust reservoirs. So that's it.
So if you're producing metallic iron grains, does that iron have to come from some population of massive stars that produce supernovae before the AGB stars appeared?
Possibly. We're not quite sure. We're still trying to determine whether or not there is enough iron, what would the condensation fraction have to be of the given the metallicities that we know in Sextans A. And it looks like we probably need more iron than what we think there should be. So something like that where we have pollution from a really early population might be what's going on here. And it's the same thing in the carbon stars. How are they making this much silica carbide, right? Where is all that silica coming from? So I think these are sort of outstanding questions that we need to answer. We're just not sure yet.
Hi, Martha. Thanks for the nice talk. Do you think trying to add observations of galactic AGB stars into this picture will be helpful, or is that just sort of too difficult to do with JWST?
Yeah, it's nearly impossible with JWST unless you're doing something like coronography, because it'll just saturate. I mean, you saturate the AGB stars in the Magellanic Clouds with JWST, so it's too sensitive of a telescope to do too much in the galaxy unless you're working with something like coronography or maybe spectroscopy, I suppose, depending on which wavelengths. Yeah, maybe with Miri spectroscopy you could do some galactic AGB stars.
Hi, great talk. I had a question. Have you looked at, I couldn't see from all the plots, have you looked at any combinations of wideband JWST filters to see if any of them are like better at separating carbon and oxygen rich?
Yeah. So we actually looked at all of them, every single filter combination that we could. And the ones that seem to do the best are these medium band filters. So this is 1.8 and 2.1 microns and 2.5 microns, 4.3 microns. Those seem to do the best. The wide filters do okay. They're not terrible, but these were the ones that we thought showed the best separation. And I will say that this paper, it's accepted, but it's not live yet on the journal's webpage. But once it is, there's going to be a catalog of all these simulations in every filter, so you can play with it.
Oh, that's awesome. Do you happen to remember off the top of your head if you looked at F182M, like that medium band?
It's right here.
I don't see. Oh, sorry. I just can't see it. Sorry.
Yeah, I made it tiny. Sorry. Yeah, it's right here.
Yeah, no, it's totally fine. Oh, awesome. Cool. Thank you.
I have a question. I'd like to know your opinion on this very extreme, very dusty stars. So we talked in the previous days about the you stated that only a few % of the population can make a lot of the dust. It can be big contributors. And in the past few days, we talked about extremely dusty stars. These were carbon, but it doesn't have to be, and the possibility that they could be made by common envelope evolution. Now, the common envelope population is small, but is of the order of a few % in terms, for example, of the one solar mass population. So if you go to low mass. So the question I have is, I guess, whether this could be binary interactions making this very extreme and yet important contributors to the dust. in maybe not in your galaxies where you need them to be a bit more massive, but in general.
Yeah, I mean, I think that's certainly a possibility. The problem with looking at these distant galaxies is that you just don't know. You kind of just have to assume that these are all single stars, which of course we know probably is not the case for most stars, right? Yeah, I mean, I think for these extreme stars, having a special situation like that to help produce even more dust, I think is probably likely.
I mean, we know that, well, I don't know how many models there are, but we know that models do not reproduce the amount of dust that you see in extremely dusty stars. So then, unless we can find better models, then you have to go to the next plan B case of having two stars.
Yeah, that could be.